for this afternoon suggests that we're supposed to do volume of fluid, but the material in the tutorial suggests that we're supposed to couple the level set with the flow solver. So I don't remember, I don't think it really matters, but since we've been working on this level set code, let's finish it up. So I suggest that we deal with the ghost fluid, we treat the, we go all the way up to the end of the story there, and then tomorrow we'll come back and see how this would look with a volume of fluid approach. So the topics for today, so first of all, we've talked yesterday morning about what needs to happen to the flow solver. We haven't talked about that in details, but we've introduced the concept of a ghost fluid method. We've introduced the concept of an in-cell reconstruction technique. We've highlighted the fact that if we know the liquid volume fraction and the gas volume fraction in each cell, we can reconstruct the density for the flow solver to use. So we have information there. We're not completely clueless regarding what the flow solver needs to go through. But the ghost fluid method in particular is not a particularly straightforward modification to the flow solver, so we'll go through the details of that together. Before we do that, we'll talk about the simpler single fluid approach to things. So basically the idea, the simplest idea you could have for coupling this interface with the flow solver would be to say that the interface acts in two ways. One is modify the density and viscosity, and second, through the addition of the surface tension force. We looked at a bunch of ways that we can implement the surface tension force on our mesh today and yesterday. So this, to some extent, we've talked about a bit already. And we have discussed about the fact that we can just create an average density and an average viscosity for our two fluids. If we use those two ideas combined together, that's it. Our flow solver is ready to go in the multi-phase environment. So essentially, we would just say, let us solve a single Navier-Stokes equation for this fluid that has this rapid change from the liquid properties to the gas properties. So we'll first introduce this approach, point out a few limitations and a few aspects, and then we'll introduce the ghost fluid approach. And the only implementation that I have in this code for today is the ghost fluid approach itself. All right, so let's do that. The topic today is the coupling with the flow solver. So let me first summarize the approaches. And we've mentioned them already, so I really don't want to spend much time on that. The first is, if you have a moving mesh method, if your mesh conforms to the shape of the interface, you essentially you don't have to do anything. So if you have a interface conforming grid, i.e. a moving mesh method, then there's no question of modifying the flow solver. The only thing you have to worry about is using the jump conditions we've derived as boundary conditions to link the two sides, the liquid to the gas side. So then you use the jump conditions across the interface. And you use them essentially as boundary conditions. So this, at this stage, has nothing to do. It's all ready to go. If you have a non-interface conforming grid, i.e., in most cases, basically in the situation where you have a static mesh, then you have to do something. And there, we mentioned this already briefly. One approach is the so-called ghost fluid method that will abbreviate as GFM. And that dates back from work of Fetkiv from 1999. We talked about this idea of an in-cell reconstruction technique. So how you can link an average density, an average velocity, an average pressure within the cell to the corresponding values in either only the liquid side or only the gas side by using the jump conditions. And this is Smilyanovsky, 96. So this approach right here is fundamentally going to be a finite difference concept. This approach is going to be a finite volume concept. But we'll first talk about a third kind of brute force version of all this. What if we just do nothing? So we'll treat the liquid and gas as one fluid, a single fluid, with a rapid change in rho and mu at the interface. That's all we're going to do. So we can write down Navier-Stokes equation. Let me see, where am I? So let me just say, let's look at this now. So if we look at the single fluid approach, we can look at the equation that we're discretizing. We want to solve d rho dt, d rho u, sorry, dt, plus divergence of rho u is equal to minus grad p plus the divergence of mu times grad u plus grad u transpose plus, say, rho g if I want to put gravity in, plus a surface tension source term. Okay, so this is my Navier-Stokes equation, and I also have a d rho dt plus divergence of rho u that we've argued is, for our treatment here, is going to be also this and this. In all of this, that density needs to be provided by the knowledge of the interface location. That density needs to be provided by the knowledge of the interface location. That viscosity needs to be provided by the knowledge of the interface location. That density needs to be provided. And that source term entirely needs to be provided. If you want to solve that equation here on the left, those densities also need to come from your level set tracking. Alternatively, if you're solving the divergence of u is equal to 0, there's no additional action required here. So everything that I have here in yellowish, it depends on the interface location. So how is that going to look? Well, will depend on the perspective we take. If we have a finite difference or a finite volume perspective, points will kind of branch off and look at both possibilities. So on the left, we'll look at the finite difference vision for this, and on the right we'll look at the finite volumes. So if I have a cell like this, if that cell is partly liquid, partly gas, in the finite difference framework, I will care about what is going on at the centroid of the cell I, comma j. So if my interface has this location separating liquid and gas, I will only care about the fact that my density should be the gas density if I'm on one side of the interface, or the liquid density if I'm on the other side. So if you have a level set, so assume a level set, let's call it phi of ij. The true solution for my pointwise density at that location is the heavy side of phi of ij times rho of the liquid plus 1 minus my heavy side of phi of ij times rho of the gas. Well, that's simple to evaluate. That boils down to my density at ij being equal to either rho gas or rho liquid, depending on whether the level set is less than 0, say, or larger than 0. And we can do the same thing with the viscosity. We can legitimately then so similarly, mu of ij will then be h of ij times mu liquid plus 1 minus h of phi of ij times mu of gas. Let's look at this perspective now let's switch perspective and think about volume method. By definition, the finite volume method will care about volume averaged data. So whether or not the centroid is in the liquid or in the gas is essentially irrelevant to a finite volume representation. So the story is going to change. Yes, I have a centroid. Yes, I can say something about the centroid. But I'm now interested in cell ij. I can still have a representation of my surface that might still look like that. But ultimately, it is volume average quantities I care about. To extract a volume average quantity here, I don't have a choice. I need to extract from my knowledge of the interface location some sort of a volume fraction data. So assume a volume fraction. I need that. I'm going to call that psi of ij to be consistent with what we've said before. But in one case, for the level set, we were okay knowing only the distance because we're working with finite differences. If we're working with finite volumes, even if we only have a level set, I'm not saying we have to use VOF in order to solve a finite in the finite volume framework. That's not what I'm saying. What I'm saying is, even if you have a level set, you have to work with volume average quantities, and that means you have to say something about the volume fraction of each phase. Have this information, then this row can be obtained from there directly. With simple integration. Same story directly by averaging this based on the volume fraction. I mentioned also that this is non-unique anymore. You can also look like this. Ij L Ij times mu. Okay, all right. So let's plug that into our equations and see what we get with a single formulation. So first of all, the first thing we're going to do is observe that our left-hand side of our Navier-Stokes equation here doesn't look very practical. Densities everywhere. So we'll take the easy way out and we'll switch to a non-conservative form. That's going to give me a du dt plus, well, it doesn't really matter. We can still leave that as a divergence of u dyadic u. It's going to be equal to minus 1 over rho grad p plus 1 over rho times the divergence of the viscosity times the gradient of u plus gradient of u transpose plus gravity plus our surface tension term divided by rho. So we've made our life easier in a simple way here. Now we have a modification of our pressure term. We still have to deal with the modified viscous term. We had that before, we still have that now. And we still have to deal with the surface tension term. Drastically reduce the number of terms that require an intrusive treatment from our level set, from our interface. So we're going to we're going to simplify our life a little bit, and we'll argue that this is not necessarily easy, but it's not necessarily the most critical term for us to get right. That it is reasonable for us to approach this by simply evaluating correctly a viscosity and a density and feeding all this to the term. This is viscosity. The viscous term is going to stabilize. It's a stabilizing term. It's not going to lead to equations blowing up. So we don't have to be too concerned with the accuracy of that term. So we'll ignore for now. Well, in fact, I probably just should treat it quickly on the side. We'll need to provide the proper viscosity. We've defined what that is, and the proper density, and we've defined what that is. We're not going to worry more than this. So this will need mu at the cell centers. At the cell centers and at the cell vertices. We haven't looked at the very detailed implementation of this in our code, so I don't want us to spend too much time on this. But this we have already. So, we're essentially all set. So we'll assume it works fine and robustly. In reality, it can become a little bit tricky for us to get very accurate results if you have highly viscous dominated flows. Then you have to be careful with what you're doing there. We'll be looking at more inertia dominated flows, so I'll kind of use that as my way of ignoring this issue. Okay. This term here, we've talked about before already. In the morning. So we've said a few things about it already, and we will go back to that term for the gauge fluid. For now, we'll leave it behind a little bit. So what we're going to go after right now is the handling of that guy. This guy, in our formulation right now, because we're using a fractional step approach with pressure projection, this step is handled through the solution of an equation for those two terms simultaneously. Right? Remember, we do a velocity prediction without pressure, and then a pressure projection where we only solve for the action of pressure. So we have a velocity prediction. Ignore pressure. And that takes our UN to a U star. But then the second step is what is going to matter to us the most. We have our pressure correction. For our pressure correction, we're solving U n plus 1 minus U star divided by the delta T is equal to minus 1 over rho grad P. Well, this 1 over rho needs to come from our level set. So, remember the way we derive the equation for the pressure is by taking the divergence of this. that gives us the divergence of un plus 1 minus the divergence of t, and that's equal to minus the divergence of 1 over rho grad p. And here, the entire point of this projection solenoidal velocities. And so the resulting equation that we're solving is the following. The divergence of 1 over grad p to 1 over the divergence of our velocity prediction. This is not the same Poisson equation we were looking at on Monday last week. The reason is we started from the non-conservative form of the equation. So we started from an equation that has a 1 over rho grad p instead of an equation that has a grad p. So we end up not with the Laplacian of p, but we end up with the divergence of the gradient, the divergence of 1 over rho times the gradient of p. So that's what we need to deal with. If we want to discretize this, we're going to have to be careful, because now our Laplace operator needs to be told something about what our density distribution is. Okay, so let's go through the simple form of this treatment. So if this is my ij cell, I will be interested in solving a 5-point Poisson equation with this time a variable coefficient on the left-hand side. This will involve the calculation of 1 over rho grad p at those cell faces. Okay, so this quantity here will need to be provided at those locations, and then we'll take the divergence of this whole thing. So with our naive approach, our pressure gradients, well, it is already, if it's computed in centered scheme, it is already at the face, fine. Our density needs to be provided at the face. So we need 1 over rho dp dx at location. So the entire thing here needs to be provided at location I plus 1/2 j, as well as I minus 1/2 and j plus 1/2 and j. And we're going to write this as a 1 over rho I plus 1/2 comma j times dp dx at I plus 1/2 comma j. And so we need to make and the simple thing you can do is simply average your density to the face. So 1/2 j plus rho I plus 1 j to get the phase value. Okay, so I'm not saying anything particularly exciting at this point. All I'm saying is, well, if we brute force our way and stick to centered schemes, this is what it's going to look like. Personally, I'm not too excited at the idea of interpolating between the density of liquid that might be 1.2 and a density of gas that might be 1.2 and a density of liquid that might be 1,000. This is not the type of interpolation that I would trust much. So that's why we're going to go to another approach pretty soon. It will save of time. I plus 1/2 j quickly, but times dp dx at I plus 1/2 j minus 1 over rho I minus 1/2 j dx at I minus 1/2 the entire thing divided by dx. That's the x component, and then the same thing in y. So I comma j plus 1/2 times dp dy I comma j plus 1/2 minus 1 over rho I comma j minus 1/2 times dp dy I comma j minus 1/2. All this over delta y, and that needs to be set to be equal to 1 over our time step size delta t times the divergence of u star at I comma j. So this is our Poisson equation. So you can assemble all this. We need to put this in the code, so we need to make this clean enough. I'll just give you the final form that you can directly put in matrix form. So that leads to 1 over delta y squared times 2 over rho I comma j plus rho I comma j minus 1 times pi j minus 1. That's the point reaching below. The point reaching to the left will be a plus 1 over delta x squared times 2 over rho I comma j plus rho I comma, I plus 1, no, minus 1, I minus 1 comma j. And that's times pi minus 1 j. Then we have the two above the diagonal term. So 1 over delta y squared times 2 over rho ij plus rho ij plus 1, and that's times pi comma j plus 1. And plus 1 over delta x squared 2 over rho I comma j plus rho I plus 1 comma j, and that's for p I plus 1 comma j. So those are the left, right, bottom, top terms, and then we need the middle diagonal for our Laplacian. So we'll have a last plus, and this one will contain, well, pretty much minus of the sum of all the other diagonals. It's still a Laplacian operator. So it's going to be a minus 1 over delta x squared times the sum of 2 of rho I comma j plus rho I plus 1 comma j plus 2 over rho I comma j plus rho I minus 1 comma j minus 1 over delta y squared, and we're done. 2 over rho I comma j plus rho I comma j plus 1 plus 2 rho I comma j plus rho I comma j minus 1. All right, and that's what multiplies ourselves, the diagonal. And that should be everything. I need my right-hand side, so this is equal to 1 over delta t times divergence of u, and u star at location I, comma j. Those being my off-diagonal coefficients. And this being my on-diagonal my main diagonal. I'm sorry, those are all diagonals. There are two upper, two lower diagonals, and the central diagonal. Okay, so this is the Poisson equation you end up solving. It's not particularly complicated. It is now a viable coefficient Poisson equation. The Laplace operator needs to be, or at least this operator is now a function of time. Okay, so at each time we get a new row, and from this new row we can recompute the operator, and then we need to invert this operator. We'll just add to this. So what do we need to this to add to this? If we're projecting at time n+1, it makes sense to add a little note. We should use rho at time n+1, meaning you need to first advect your level set or your VOF to get your new density, and then use this for the projection to be completely consistent, since the projection is at time n+1. And then don't forget, this is, so once you've done that, you solve the Poisson equation. This is deserving of a little comment. This Poisson equation is going to be pretty ugly, because now it is this Poisson equation is going to have viable coefficients that are going to vary by, again, if we go from liquid to gas, 1 over rho gas is on the order of 1, 1 over rho liquid is on the order of 10 to minus 3. Therefore, we have 3 orders of magnitude difference between those coefficients on one side and the other side of the interface. So that's going to be a tough equation to solve. If you are happy with, say, a simple Gauss-Seidel or a conjugate gradient type of solver with a constant coefficient version of a constant coefficient solver, it is very likely that this won't do the trick anymore, and you would need to have more involved linear solvers. Okay, are we done? Yeah, we're almost done. We just need to correct. Last step is to correct the velocity. Once you know the new pressure, and that involves making use of that equation that we wrote already. The pressure is going to show up in that as well. So what you're going to apply is add to u star, well, subtract really, delta t times 1 over rho grad p. So this quantity is exactly the same than the one we've discretized right here. This is the same story. So no difference here. We can write one so we can say, for example, that u at face I plus 1/2 comma j at time n+1 is going to be u star at phase I plus 1/2 comma j minus delta t times 2 over rho I comma j plus rho I plus 1 comma j times pi plus 1 comma j minus pi comma j divided by grad x, delta x. Okay, and same for v. Okay, so that's the overall approach. So we can summarize the scheme that we would need to solve, the overall framework we need to solve for this, from the perspective of the full coupling. So coupling of flow solver to either a VOF or a level set. Step 0, you initialize everything. So you're going to initialize U and either phi if you're using a level set, or psi if you're using volume of fluid. I shouldn't write this like this is confusing. So phi or psi. First, you're going to advance using the old velocity your interface representation. So advance psi or phi using un. So you're going to take either psi from n and bring it to psi of n plus 1, or phi of n and turn it into phi of n plus 1. Now you can evaluate everything you might need. You can use psi at n or n plus 1, or phi at n or n plus 1 to obtain rho at n or n plus 1, mu at n or n plus 1. Then you perform your velocity prediction. So that brings you from un to u star. You form your Poisson equation. Since it's a function of rho, you need to update your operator and solve using rho at time n plus 1. And then you correct. So that gives you p n plus 1, by the way. Correct using, I should say correct the velocity using rho n plus 1 and p n plus 1. So that corresponds to bringing u star and turning it into u n plus 1. Okay. At this point, we have a first order time integration you could say, so I'll just make the point here that at that step, we've used the old velocity, and it would have been useful to use an n plus 1/2 velocity to obtain second order accuracy in time. So you can subiterate. Now that you know un plus 1, you can average un plus 1 and un, form un plus 1/2, and now you can go through your transport again. This time you'll have a second order estimate in time of your new interface position. So you can subiterate using un plus 1/2 is equal to 1/2 of un plus un plus 1 in step 1 to obtain order delta t squared. So I think we've said pretty much everything here. The only thing that I've passed is doing the same thing for the viscosity, but again, this is no reason to lose sleep. Any questions on this? Is that obvious at this point that we can just plug this into the code? So the big problem I have with this, and the reason why we're not ultimately going to do this, is the fact, let me see, where am I here? There we go. The big problem that you should have with this is any place where something like this is performed, that should concern you a lot. Because it is unclear why you should have, so again, imagine liquid and a gas that's going to give you lots and lots of 500 coefficients for no clear, or at least not clear to me, reasons. So instead of trying to interpolate across a discontinuous quantity, we're going to try to see what would happen if we were to not have a single attempt of reaching to the other side. Okay? So this, by the way, this works. This is fine. You can use this. There's limitations to this. It doesn't work under all conditions, in particular, especially if your density has been spread over several cells, the higher the density ratio. So if this rho has been obtained through a smeared out heaviside defined from the level set, you will tend to see a somewhat unstable behavior that will develop, especially for high density ratios. But fundamentally, this is okay. This is okay. Any type of instability that might arise due to high density ratios, we're not going to fix in what we're going to talk about right now. So right now, what we're going to try to do is avoid any type of explicit interpolation from a high value to a low value of density. And in the meantime, in the process, we're also going to say that so far we haven't discussed, we've left this guy behind a little bit, so we'll introduce this guy as well. So because we're going to go after a completely discontinuous formulation, we're not going to go after that representation of the surface tension, but instead we're going to go after the discontinuous pressure representation of surface tension. So remember, sigma times kappa is the jump of pressure. If now I go after a discontinuous solution of my pressure equation, I should be able to account for a discontinuous pressure solution, and that should automatically handle this. So that's what we're going to do with the so-called ghost fluid method. So let me conclude that by saying that works. But we're going to go to an alternative approach. That's going to be the ghost fluid method. The classical reference for this is Fetke-Vedel 99. It is not really the most appropriate reference for what we're going to talk about right here. Fetkiv et al. 99 looks at the ghost fluid idea in the context of a compressible flow. We're doing compressible flows here. So we're interested, as far as this representation is concerned, again, if you allow me to not worry too much about the viscous term, the essence of the discontinuity here is in the fact that one of a rho is discontinuous, and this guy we can embed in here and say that the pressure is discontinuous. We can boil the entire discontinuity of the problem into the pressure projection problem. So what matters to us is the solution of a discontinuous pressure Poisson equation. Well, the discontinuous pressure Poisson equation has been discussed more explicitly by Liu et al. And that's 2000. I think the paper is in your 3? Yeah, 3 or 4 or something like this. Let's cut it in the middle. There's another paper by Kang et al. They're all from Fetkiv's group, so they're all Kang at Fetkiv. There's one Liu and Kang and Fetkiv. The other one is Kang and Liu and Fetkiv. Okay, so the idea for this is going to be to think about what a liquid value would look like. For any value, we're going to think about what the liquid value would look like on the gas side and what the gas value would look like on the liquid side. So we'll think about those ghost fluids that would subsist on the side on which they're not. So let me very grossly sketch this, and then we'll simplify our life a bit almost right away. So say this is my interface. Here's the main idea. Those cells are green cells, say, I don't know, liquid. Again, the ghost fluid method is a method that looks at the problem from a finite difference perspective. So as long as my cell center is in the liquid, I'll say it's a liquid cell. And those are gas values. Well, I'll define some ghost gas value in my liquid region, which I'll designate with those open symbols. And I will similarly define a ghost liquid value on my gas side. So let me explain my nomenclature here. This is a ghost liquid value. This is a true liquid point, and value I should say point really. This is a ghost gas point, and this is a true gas point. Okay, so far easy enough, right? Nothing too complicated. So we talked about methods that allow you, again, I want to really highlight, this is a finite difference scheme. So this idea is not complicated. And in fact, we talked about the type of tools that would be required to take liquid data on the liquid side and extend that towards the gas side this morning. We talked about the fast marching method. We talked about this Hamilton-Jacobi equation, where on the right-hand side is the gradient of eta dotted with the gradient of g is equal to 0. Those type of relations would allow us to take data here and extend that data normally to the interface onto the other side. So this is the type of thing you can do. It's not complicated to take the liquid, remove the gas, extend the liquid to the other side, and call that your ghost result. since the only thing we need to worry about here is arguably the Poisson equation, we can take a significant shortcut and save ourselves the trouble of actually creating all this mess. So instead of creating all that, we'll think a priori with our Taylor series expansions in the finite difference framework, and we'll think about what it means for us to have those fictitious fluids. So consider a quantity F. Okay? Well, if I have generated my fictitious fluids, I'm now free. I can now define the jump of F anywhere. This is what I've gained. So far we've talked about the jump of a quantity at the interface. Right? This quantity F L minus Fg at gamma, the interface. Well, I can do that anywhere I want now. Okay? At any location, I can look at the differences. So, and this jump here, let's clarify, we're talking about Fl minus, or I think I'm going to be using little l's, Fl minus Fg. So, let's start thinking about manipulating this a little bit. So let's do a Taylor series expansion. Of this quantity F. It makes sense to start the Taylor series at the interface, since this is where the jump is going to be defined. So the jump at the interface, I can extend that, and I'll do it in 1D. We're not going to worry with 3D. We'll just differentiate the Laplace equation in 1D. And now if I go through the Taylor series expansion, I'll get the jump of F at gamma plus the distance to gamma times the jump of the derivative of F at gamma, and I can keep on going. Let's add a term times 1/2 x minus x gamma squared times this time the jump of the second order derivative of F in x at gamma. I can keep on going, but I'll stop here with an order x minus x gamma to the cubed power. So this is a very general relation. I can make use of this. And by the way, you might say, well, how do you know how to use both jumps? And how do you know how to do a Taylor series of a jump? What does it mean? Well, the jump is just the difference. You do a Taylor series of the liquid quantity, a Taylor series of the gas quantity, and you do the difference, period. Okay, so nothing magical here, that just falls right out. So let's think about how we're going to be using this. If I'm interested in differentiating, so now consider a Laplace or a Laplacian. So I'm going to look at a little simple stencil, and we'll first look at what's going to make this whole thing work, and then we'll go through the derivation. So xi minus 1, xi, and xi plus 1. And I'll assume that I have an interface at x gamma that separates the gas from the liquid. If I want to estimate between cell I and cell I plus 1, if I want to estimate the gradient, I would estimate, or let's do, in fact, you know what, let's not do, sorry, let's just consider a gradient, a simple gradient. We'll do a centered gradient. So if I want df dx at cell I, and say I want this df dx, I want it in the gas. Why do I want it in the gas? Well, because in the finite difference framework, That point is sitting in the gas, and therefore I should go after the gas value. It's easy to write. It's going to be F in the gas at I plus 1 minus F in the gas at I minus 1, divided by 2 delta x plus an error of order delta x squared. Okay? No surprise here. This is just second order estimate of my derivative. Obviously, point xi plus 1 is not in the gas. So I do not know this. This value is not available to me. What I have, however, is FL I plus 1. So we'll make use of this. Okay, so this guy is problematic. So we'll replace it by an F liquid at I plus 1. I have this F liquid. This is fine. This is part of my solution. But now I will need to subtract from it my jump. So I will need to subtract the jump of F at location I plus 1. And then I can continue with my original discretization. And in this, I will need to prescribe what the jump at I plus 1 is. But I have this Taylor series available to help me do that. So I can directly relate this to the jump of F at gamma, which I would expect in general that we would know. I would think that the physical set of equations we're solving will tell us what that jump is, plus an x sub I plus 1 minus x sub gamma of our derivative of the jump at gamma plus an order of x I plus 1 minus x gamma squared, close the parentheses. So that's the essence of the idea we're going to use. We're going to go through our discretization within a single phase. Every time we find that our phase is not the one that we expect to find at our grid point, we'll make use of this jump right where the grid point sits. And then this jump we'll have to express based on what's going on at the interface, which will assume that we can know readily from the equations we're solving. And then we'll have to deal with this extra term. And we'll make it more explicit what to do with this. We'll have to invoke a model to handle this. Okay, so is the idea making sense to everyone? We're all on the same page. So now let's just make use of this to solve or to express a perfectly sharp discretization of the Laplace equation. So we looked at this general gradient. Now let's turn our attention to the pressure. The pressure Laplacian, again, we derived it as divergence of 1 over rho grad P. And in order to kill two birds with one stone, we're not going to worry about discretizing differently the surface tension. We're going to say explicitly that since we're going after a discontinuous method, let us solve with this explicit constraint that the pressure should be discontinuous based on what the local sigma times kappa is. Okay, so we'll create a little sketch again. And we'll consider one specific case. But then the implementation will need to be capable of handling all the cases. So again, I will assume that my interface is right here at location x sub gamma. And I will be solving my Laplacian by first expressing dp dx at I minus 1/2 and dp dx at I plus 1/2. And then finally I need to make a choice. It doesn't really matter, but we'll assume that this is the gas side and this is the liquid side. When I say it doesn't matter, it doesn't mean that discretization is the same, but you can carry out the derivation in both cases. You'll find different answers, but you can obtain them. So we'll start with the obvious. I want d over dx of 1 over rho of dp dx. And yeah, I don't know if I said that, but I want a 1D discretization. We're not going to worry more than that. I want, because of the configuration, I'm going to be computing this in the gas. Right? My cell I is in the gas, so I want the gas value of this. And I want the gas value at cell I, at point x sub I. This can be discretized with second order accuracy as follows. The P gas at I plus 1 minus 2 P gas at 1 plus P gas at I minus 1 over another 2, no, over delta x squared. And this is a order delta x squared discretization. Okay, no complaints? It's all good. Now obviously this term is, again, not something we can compute. So we'll need to replace the point that we don't know. So we need to replace the gas value at I plus 1 by something we know, which is the liquid value at I plus 1. And we do that by subtracting the jump at I plus 1. So ultimately our discretization now is this. 1 over rho dp dx and we know how to compute the jump. The jump is the jump at the interface. And then the extra term in our Taylor series, if we want to go to second order accuracy, depends on the jump of the pressure gradient at the interface. This entire package is second order accurate. So, are we done? This I can compute. This I have an expression for. This I can compute. This I can compute. The expression for this is this. This I'm assuming that I know. This is my sigma times kappa. This I know. This I know from my interface treatment. What about this? What can I say about this? Do we know anything a priori about the gradient of the pressure and the jump of the gradient of pressure? Say it again? Well, the surface tension tells us something about the jump of pressure, not directly about the jump of pressure gradients. But so yeah, this is a problematic term. So if you'll allow me a few assumptions, we'll take care of it, but we have to make a few assumptions. So this is still, at this point, unclosed, unfortunately. So if I neglect viscosity, and if I still assume a continuous velocity at the interface, then those two assumptions allow me to write that du dt plus u dot grad u is equal to minus 1 over rho grad p, right? And this is the local material derivative of the velocity. If my velocity is continuous, the argument would be that this would be a continuous term, and that therefore this term should also be continuous. So there's no jump of u. We would argue from that there's no jump in the time derivative of u, and as a result there is no jump in the, I'm sorry, there's a minus that I'm missing here, and therefore there's no jump of that right hand side. Okay, so from that, so jump of gamma, jump at gamma of u is equal to 0 implies that the jump of du dt at gamma is equal to 0, which implies that the jump of 1 over rho grad p is equal to 0. This is not an exact treatment. Why is this not an exact treatment? Sure, the density is there, but still, I stick to, if there's no jump on the left-hand side, then there's no jump on the right-hand side, because the left-hand side is equal to the right-hand side. So that, the presence of the density, yes, the density is discontinuous. That's kind of the point. We're saying that even though the discontinuity, there is clearly a discontinuity between 1 over rho on the left and on the right, the pressure gradient has to adjust to that instantaneously, or else our velocity would have to be discontinuous. So this is a reasonable statement. It's not grossly wrong in any way. Why is it not perfect? And really I should put approximately equal to 0. Well, because we've made assumptions. Well, the assumption that the velocity is continuous at the interface is not really an assumption. It is the fact that the velocity is continuous at the interface, but we've neglected viscosity. If you reintroduce viscosity, you have an extra right-hand side. Well, this extra right-hand side, it has extra discontinuities because it contains a 1 over rho that's discontinuous times the divergence of a discontinuous mu. And then what's next in this term is the symmetric part of the velocity gradient tensor. The velocity gradient is not continuous. So this extra term has in fact extra jumps, which means that this jump here should in fact be equal to minus the jump of this extra term. So this essentially makes sense if you're not completely in a situation where the viscous stresses dominate. If this is the case, in fact, I don't know. I don't know if this approach has ever been used to look at creeping flow conditions. So I don't know if it would work anymore. But certainly, at least I'll say that I don't know about you, but I care more about high Reynolds number flows for which this is reasonable. Okay, so what do we do with this? what we're going to do with this is simple. We'll derive a little rule for ourselves. What is the jump of A times B? Well, the jump of A times B is A liquid, B liquid, minus A gas, B gas. And now, for fun, we'll add and subtract the same quantity. So it's going to be A liquid, B liquid. I will say minus A liquid, B gas, plus A liquid, B gas, minus A gas, B gas. Have I lost everyone? If I have, I'm sorry. All I've done is I kept the first and the last term, right? The liquid minus the gas, that's all we're doing here. So the first and the last term have been unchanged. In the middle, I've just added the mixed terms, liquid gas terms, plus, minus of the same term. So I haven't changed anything. But now we're going to be able to collect and factorize. So that's going to be equal to, if I take these two together, that will give me A liquid times B liquid minus B gas. If I factorize, this is now the jump in B. And then plus, the other one should be B gas times the jump of A. So we can expand those expressions. So if we apply that, if I apply this idea to our model that says that 1 over rho dp dx at the interface should be approximately 0, what we find is that this is 1 over rho liquid, okay, A liquid times the jump of dp dx at the interface, plus dp dx in the gas at the interface times the jump of 1 over rho. Right, I'm just applying the jump of AB is equal to AL times the jump of B plus B gas times the jump of A. I'm applying this rule to expand this, and I get this relation. And that means what? Well, that means that if I want to know my jump in pressure gradient, I can relate it to the local density, the jump in density, and the local one-sided gradient, the gradient in either the liquid or in the gas. This is not the only expression. You can obviously write the symmetric. If instead of subtracting by ALB gas, I had subtracted by A gas B liquid, I would have the symmetric expression here that would replace here the liquid by the gas and the gas by the liquid. So you can do the same thing and obtain an expression based on the liquid gradient instead of the gas gradient. So here, if I bring that together, what I conclude is that I can approximate dp dx, the jump of that at gamma. I can approximate that as minus the jump in the liquid, no, sorry, the density in the liquid times the jump in 1 over rho. I don't need to say that I want the jump of 1 over rho at the interface because my rho's are constant. So the jump of 1 over rho is the same anywhere I evaluate it. Times dp dx in the gas at location gamma. And if I had I used the other expression, the other way of expanding this, I would have obtained the following thing. I would have obtained minus rho gas times 1 over rho jump dp dx in the liquid at the interface. So that relation is kind of a big deal because that relation now allows me to say something very concrete about my jump in derivative, and I can relate it to the non-jumpy derivative. So if I go back to where we left off at the point where we were evaluating the jump of P at I plus 1. right? We were right here. We said this is our expression. Now I can rewrite that term and carry this further. And we'll essentially bring this to its conclusion quickly. Therefore, the jump of P at I plus 1 now can be approximated as the jump of P at the interface. And then I go back to my Taylor series times minus rho L times the jump of 1 over rho times dP dx in the gas at the interface plus an order delta x squared error. So now everything that we have is expressed in terms of pretty reasonable quantities that we can hope to access. We'll take one shortcut that we don't absolutely require, but that will make our life infinitely easier in terms of the derivation. This guy is at gamma. This guy shows up in that calculation wherein dP dx is at I plus 1/2. So it would be a lot easier if we could simply compute this guy at I plus 1/2. So we'll make this simplification. It's where we officially give up the second order accuracy, and this is an explicit first order error. So I propose we approximate dP dx in the gas at the interface by dP dx in the gas, but now at I plus 1/2. Doing that allows us to reconnect with the rest of the discretization. We now have, again, a centered, we can use a centered finite difference scheme to estimate this. So we can say the jump of P at location I plus 1 is now approximately the jump of P at gamma minus x sub I plus 1 minus x sub gamma times rho L times 1 over rho times P gas at I plus 1 minus P gas at I over delta x. What have I done? I took this here, I replaced it by the value at the face, and then I directly replaced this by its discretization. This is P at I plus 1 minus P at I divided by delta x. That's how I get to this expression. So now, unfortunately, because we've misplaced our gradient, this is only an order delta x approximation. If I go back a bit, and if we look at the schematics, what have we done? We said that it's the pressure jump and the pressure gradient jump here that matters. We took the pressure jump here, and we said that really the pressure gradient jump here we could estimate using this closest face. So this is not an enormous error. We know that by at most we have a half cell. We've misplaced our gradient by a half cell. Okay, are we done? This we have. This I know. I know. This I don't know. All right? I plus 1 is in the liquid. So we're almost done, but we have to again go through the frustration of observing that we don't know this guy, and so I need to jump again. I can only write this as P liquid at I plus 1, from which I'm subtracting the jump at I plus 1, minus P gas at I. But this time it looks like we're done. Because yes, I've had to use the jump again, but that jump by definition is the same as this guy. So now, okay, my jump shows up on the left and on the right, but I can bring that back to the other side, clean it up, and have a closed expression of my jump away from my interface in terms of the jump at the interface, how far away I am from the interface, the local non-trivial distribution of densities, and my local distribution of pressures, which are liquid wherever I have liquid and gas wherever I have gas. So now I can just invert this. So let me write this out, and then we're done. This is P at I plus 1, the jump. This is equal, or we find, upon carrying out the manipulation, we get a rho gas. The math is not complicated, but we've done enough writing that I'll just take the shortcut of giving you the answer. So we end up with a rho factor that multiplies the jump at the interface, and then another rho factor that multiplies a pressure gradient taken across my change in phase. Thank you very much. All right, in this I've introduced rho star. Rho star is equal to rho gas times theta plus rho liquid times 1 minus theta. And what is theta? Well, theta is my stencil fraction that's sitting in the liquid. So theta here is x sub, I'm sorry, it's in fact here the gas fraction. So it's x sub gamma minus x sub I over x sub I plus 1 minus x sub I. There we go. So nothing in everything we did here assumed any type of interpolation, any type of attempt to find some average quantity between left and right. We have this piece of information that requires the knowledge of what x gamma is. What is x gamma? It is the position of the interface along the length of our pressure stencil. So it's very clearly defined. If I'm sitting at a cell center x sub I and a neighboring cell center x sub I plus 1, if the product of my two level sets is negative, I necessarily have at some place in between an x gamma. If the product is positive, I do not, and I do not need to worry about any of that. Then I will need to build an effective density, and then I can use all this to express what is my jump. Once I have my jump, I can now compute my full Laplacian. So the last thing we can say with all this is now back to our full Laplacian. It's going to be a d over dx of 1 over rho times dp dx in the gas at location I. This is equal to 1 over rho star times P liquid at I plus 1 minus P gas at I minus 1 over rho gas of P gas at I minus P gas at I minus 1, the entire thing over delta x squared. And from that, I have subtracted the jump. That is, at this point, it's been brought down to location gamma over rho star times delta x squared. And we are done. So this is our ghost fluid pressure Poisson equation. It has, yes, some sort of an effectively interpolated density, but it never shows up because we've actively decided, let us interpolate the density to that from that position to that position. That's not why it shows up here. It shows up only because we've combined Taylor series that sometimes we multiply by rho, sometimes by rho gas, sometimes by rho liquid. And so there's no effective interpolation that led us to have this effective rho star. It uses locally only the pressure values that correspond to the phase that we expect to have, period. And then everywhere where the phase that we expect is not the one in which we want to compute a Laplacian, we will have an extra term that will show up. So what does it mean? Well, it means that as far as the pressure operator is going to be concerned, we're going to need to be careful about two things. One will be the calculation of an appropriate density. It will not be the simple half of density on one side and the density on the other side. And then every time we end up going across, our stencil ends up going across the interface, we'll need to have an extra right-hand side term in our Poisson equation. We'll have this extra guy that is not going to be part of our stencil, it's just going to be an extra source term. So we need so at each time step, every time we get a new density and a new interface position, we will need to update our Laplacian. Surface tension shows up as extra right-hand side terms. Effectively, this is first order only. Unfortunately. It gives us a sharp treatment in the sense that there's no interpolation, extrapolation, there's none of that that's being done. And then there's one last very interesting consequence of this discretization that we'll see briefly with the test cases we're going to do. Because our surface tension is written as part of our pressure solution, the surface tension force is going to discretely be consistent with the pressure gradient. They're going to be the same thing. We're going to say that a pressure gradient, we're going to say that surface tension will essentially show up in the form of an extra pressure gradient. Why does it matter? Well, it matters because if you think about what a static droplet is, well, a static droplet is globally static because the surface tension force balances itself out everywhere throughout the entire surface. But there's one extra term that shows up, right? If I take a little chunk of surface, well, I can sketch instead of hand waving my argument. if I take a little chunk of surface, my surface tension pulls in that direction here and in that direction here. So that gives me a net amount of pulling of this interface towards the inside. Well, that's exactly compensated by the fact that the pressure inside is increased. So a static drop is static because my surface tension is pulling exactly the same way on both sides, and the imbalance that remains, so I have the same sigma times kappa pulling on the two directions, and the imbalance that remains is exactly compensated by the extra pressure from the inside. Well, if I want this to be possible, if I want the pressure gradient to be able to exactly compensate my surface tension source term, I need a certain type of discretization where it is in fact possible for my pressure gradient to be exactly compatible with the surface tension term. That sounds kind of a silly statement, but it's not guaranteed. Writing a discrete pressure gradient gives me access to a finite number to a subset of the possible forces. So you can conceive of a way of writing a surface tension force that could never be possibly balanced by a pressure gradient. But because here our surface tension shows up directly in our pressure Poisson equation, it will come into action from directly the action of pressure gradient, and therefore it will be discretely possible for surface tension to be counteracted by the pressure gradient. What that means is, with this system, and pretty uniquely with this system, if I set my curvature to be a constant over a closed surface, I should have a perfectly static answer. I should be able to simply predict a pressure rise inside my closed object and nothing else. There should be no flow induced. So ST is equivalent to gradient of pressure. The implication is an exact constant kappa leads to no flow. And that's a big deal, the idea of potentially being able to look at a perfectly static droplet. All right. Any questions on this stuff? Yes?
How do we obtain curvature at the interface? Do we interpolate from the surface centers?
Yeah, so we're going to look at that right now. Yes, we will have to do something here. I forgot to talk about this. This is the jump of P at gamma. That is the jump of the pressure at the location of the interface. Our mesh never really goes through the exact location of the interface, so we'll need to do an interpolation there. And so we'll do that. We'll actively, I think what I have in the code is a simple linear interpolation. So I'll estimate my jump in the cells nearest to the interface, but then I will use the knowledge of what x gamma is, so I'll use this theta in order to interpolate my sigma times kappa between my two nearest cells. I bring this information right at the interface. Yes. Other questions? Okay. So let's move to the code. So this is one of the biggest changes that we've looked at so far. The main reason for the fact that it's a significant amount of changes is the fact that, like we said, we need now to say something about the pressure. We need to modify a pressure equation. We need to modify, so, oh, by the way, I forgot one thing. The other thing we wrote here is the pressure Poisson equation. We will always have to do the same thing with the correction. So computing the pressure gradient and adding it on our velocity field will require the same treatment. It's just much shorter, and it's a subset of what we've done, so it's not too complicated. All right, let's see, where are we? Okay. So I think this is T8, yes. Okay, so let's go to the first directory. I took this problem in 2 steps. The first, so here the derivation, it was easier to just do everything at the same time. But really there's two separate questions. One is, what is the effect of having a non-zero jump of pressure? And the other one is, what is the effect of having a different 1/ρ on each side? The first problem I've handled is in the directory 1. And that is, what is the effect of imposing a surface tension jump? Okay, so the first problem has constant density. We're going to look at the demo flow stuff, I think. I need to remind myself. Most of the changes are in level set of F90, but I think there are a few elsewhere. There need to be a few elsewhere. Well, in fact, let me do an open diff so that I don't miss out on anything. Okay. So it's not in pressure of F90 that the main change is. The main change, well, first of all, there's one change that's important and that needs to be said. I've turned back on the flow solver, right? Yesterday everything was turned off. So the flow solver is turned on. We called the level set right before the flow solver. So this is exactly the scheme that we summarized half an hour ago. Using velocity at n, we advance the level set from n to n+1. And then we get a new density, and then we use this to advance our velocity and do our pressure projection. So one little note here. That's my pressure Laplacian in a single phase environment. If I don't have to worry about any of this, my pressure Laplacian are just these diagonals. I have a +1/d², -2/d², +1/d². Basically, pointed to the left, to the right, above, below, they all have +1/d², and the point in the middle has twice -2/d². So that's my basic Laplacian. We're going to have to modify that. The main thing we're going to be changing is going to be the pressure step. Because with the way we've set up our problem. Oh, and I should say one more thing. We're going to ignore anything related to viscosity. So I'm assuming that the viscosity is continuous. I'll do nothing to the viscosity. Okay, so I have a pure single phase treatment of viscosity at this point. It wouldn't be complicated to change. I just thought this would be more important to talk about the ghost fluid. So then the only thing for us that needs to be changed is not in the pressure, in the velocity prediction, but in the pressure correction. And this is what I do. after having done after having enforced global mass conservation, remember we talked about that earlier last week, I compute my divergence, which is my right-hand side of my Poisson equation, but then I stop and I go to another solver. So if you use the level set, I'm going to rely on the gauge fluid method approach to solving my pressure equation, and I will return from this. So I bypass this entire thing. Okay? So now let's take a look at what's left. In the level set, I can tell you, well, we'll talk about that later. The code is the same as before. We have our initialization. This is the we know we looked at yesterday. This is our normal calculation. Remember, we looked already at the curvature calculation. This is just the divergence of the normal. So we have our curvature. This is my gauge fluid method for the pressure. There are multiple steps. The first step is to recompute on the fly my Laplacian operator to make it aware of my change in density, but I've said I'm not going to worry about my density change here. So my pressure equation is going to remain the same for now. Then I'm going to make it aware of the extra right-hand side, which looks like simply sigma, a coefficient I'm defining in the top of my file, times my curvature that I've computed already. Okay? How is the scheme going to work? Well, it's not very complicated. And it can be written more efficiently than this, but I want to make it easy to understand. I will loop over my entire domain. The ij indicates the point where I'm examining my Laplacian. At that point, I'm going to store and remember that G1 is my distance to my interface, so this is my level set locally. If it's positive, I'm on one side, negative, I'm on the other side. And J1 contains the jump at that location. This is sigma times the curvature of that location. So nothing too exciting right here. Then I'm going to go through what we derived in the most manual way possible. I'm sitting at ij. I'm going to look above, below, well, basically left, right, above, below. Or sorry, left, right, below, above. Okay, so I'm going to traverse my stencil. And I'm going to look at whether my neighboring point is not in my phase. If it is not in my phase, the treatment we wrote for the past hour will have to be invoked. And that will lead, if you remember right here, I had this extra minus jump of p at gamma over delta x squared times rho star. Again, rho star is not a question here. Rho is the same everywhere. But I'll have this extra term that I'll move to the right-hand side of my equation. So I'll add an extra right-hand side term. So if I'm outside, what am I saying? If wall are outside domain, edge, or... okay. Basically, I'm saying I don't need to do anything once if I'm sitting already against the wall, I know that, that my Poisson equation has a Neumann condition. I don't need to do anything there, so I'll skip those cells. Oh, I'm sorry, this is the main structure. So this loops in dimension 1 and 2, direction +1, -1. So what that does is it goes left, right, bottom, top. II, JJ is my new position of my second point in the stencil. If that point is outside, I don't need to worry about it. Otherwise, I look at the value of my level set at that second point, and I also store the jump at that point. Okay, so I'm sitting at ij, I have my level set, my jump, and I go to one of the neighboring points and I look at the level set and the jump. And then the question is, do I have an interface between those points? Well, the question here is, here I'm really, again, you can write this more efficiently, but I'm just going to say, if both the level set values are greater or equal than 0, I'm going to say that they're both on the same side, and therefore I don't need to worry about the jump. And I set my jump to 0. If they're both negative, then they're both on the same side. I don't need to worry about anything, and I set my jump to 0. Otherwise, I'm in between, and I know that the point that's not me, so not ij, but iijj, that other point, my neighbor, I'll need to flip it to my phase. And in doing so, I'll need to add this jump. So first of all, the jump I need to know it at gamma. So that's the question you were asking a minute ago. To do this, I'm simply going to do a linear interpolation. I know jump 1, jump 2. I know distance 2, distance 1. And so I'm just going to do a linear interpolation using my level set. Okay? But then, depending on whether I go from liquid to gas phase or gas to liquid phase, I will either need to add the jump or subtract the jump. And so, in fact, I will need to subtract the jump if my second point is in the negative level set side. And then what I do is I just add this to my right-hand side. So I will increment my right-hand side. At this point, my right-hand side is stored in this divergence array. I computed the divergence of my velocity. So I add to my divergence array, and in fact, I wouldn't need to do any of those tests. I'm leaving those tests here because they're going to show up as soon as we start looking at the variable density problem. But the only thing I need to do, I do the same thing everywhere here. If I have a non-zero jump, then I need to add this jump to my divergence. The jump looks like dt times the jump divided by dx squared. That's it. Okay, so this is exactly what we wrote. That's my new, so that's just modified the right-hand side of my equation. The Laplacian has not changed. With that resulting equation, I call my solver. That's not changed. I'm going to use the exact same solver. And then I need to correct the velocity. Correcting the velocity, again, will involve computing a pressure gradient. If I compute a pressure gradient, I need to be careful about using the same size, the same phase pressures. And so I need to account for jumps again. So I go through the same process right here. I loop over my domain. I'm going to be computing the gradient between cell I and cell I minus 1 in order to update my velocity at I minus 1/2. If they're both on the same side, I won't have a jump. If they're both on the other side, but again the same side, they won't have a jump. Otherwise, I need to reinterpolate my jump. And then when I compute the pressure gradient and apply it, I just do u is equal to u minus delta p times p minus p over d, except now I have this extra jump. So that's exactly the equations we derived. We need to be careful about the existence of that jump to bring us from the liquid to the gas or gas to the liquid as needed. This was for u. We do the same thing for the velocity in the vertical direction. This time we're going to be looking between cell j and cell j minus 1. If j minus 1 is not the same phase as myself, I'll need to add or subtract the jump depending on my sign. And then that's what I add to my pressure gradient. Does that make sense? Is that meaningful to everyone? The last step I had in my pressure solver was for monitoring. Once I'm done solving all this, I want to recompute the divergence to check that my divergence is well. So I had that in a single phase solver as well. Okay, so now we're accounting for the local effect of our curvature. So let us first check what happens if I run with a simple circle. Okay, so my domain is a square domain. I don't remember what I have, but I have no flow. I'm just going to place a circle in the middle, radius 0.15. Okay, so my g is 0.15 minus square root of my position. So let's try running this. Oops. All right, so here we are. Let me restart inside, I think. It's not supposed to be so slow. What happened? Okay, good. So you notice that I changed a little bit the initial condition compared to what I had by default in the code. I want to make a specific point with that, although I'm not sure how this is going to work, but let's see. Let us look at first the initial G field. That's my initial G field. I will extract an isosurface from this at 0 so that we can look at our nice little circle. Okay. Then well, it looks pretty good. Then what we're going to do is look at coloring all this by the velocity. Let's look first at the curvature. So what should be the curvature? The radius is 0.15. 1 over 0.15 should be 6.6. Let's check that this is the case. If I plot my curvature between 4 and 10, yes, you can see that we're somewhere right around 6. So our curvature calculation is not unreasonable. Now let's look at our velocity field. The initial velocity field is 0. Let's take a step forward and let's look at what happens. So this is my velocity field. So what's going on here? Well, you know, but so let me plot this velocity field in a way that's more visible. So let's look at what we have. I turn on the flow. And you can see that we establish a flow field. So what would be the exact solution here? Right, we're solving Navier-Stokes equations with surface tension. There's some viscosity in the problem. But we're solving Navier-Stokes. We're placing a perfect circle on our mesh, and we're turning on the effect of surface tension, and that's what we're doing. So what happens if I put a circle under tension? Now, this should just be a simple bubble or drop type of solution, right? I have a circle under tension. This is a perfect circle. A perfect circle is characterized by a constant curvature. My curvature is constant. The amount of pulling is the same everywhere. I should just get no flow at all, no imbalance. However, I should have a pressure rise inside. Well, let's check our pressure. Hooray. So yes, we see a pressure rise. Okay, if I create an elevated surface using pressure, yes, I have a nice little pressure jump like this. Initially, my pressure is not that, and then, boom, my pressure rises. So that's fine. Our surface tension is putting the fluid in the middle in an elevated pressure state. That corresponds to what we would hope. But we shouldn't have any flow. So why are we seeing this flow? Right, you can clearly see this nice little vibration. Our interface kind of oscillates. Well, the interface oscillates because so in a general sense, there can be two reasons for which an exact circle would lead to a vibrating flow field. Reason one, what I was hinting at before, if my surface tension and pressure gradient are not compatible, it is never going to be possible for me to find a pressure rise in the middle that would give rise to a pressure gradient that would exactly compensate the surface tension force. This would be what we would call an imbalanced surface tension implementation. This is not the case. Our surface tension shows up through the pressure, so they are necessarily going to be compatible. So what's going to happen here is that what's left for us to explain this is that our curvature is inaccurate. That yes, a circle should have a perfectly constant curvature, but our true curvature is not perfectly constant. And as a result, places that have somewhat higher curvature experience somewhat higher pressure, and they try to flatten more, and that leads to a higher curvature in neighboring regions that then try to flatten more, and we end up with those small oscillations. They're not large in this problem. They're in fact surprisingly small. If this hypothesis is correct, then if I were to set my curvature to an exact value, I should see exactly no flow. Let's check. It's an easy check to make. Let me scroll back down to where I compute the curvature. There you go, level set curvature. This is where this is calculated. I'll set the curvature everywhere to whatever this was supposed to be, 6.6666, something like this. And let's see if that runs, and let's see what happens. I'm now looking at 10 to the minus 8 flow, or 10 to minus 7 flow. The reason why this is not better is because I do a finite number of pressure steps, so I do end up accumulating some error. But if I go here and jump to this and take one step, the velocity just disappears. So if I prescribe a constant curvature, this goes through the method, in turn gives you absolutely no flow. You can do a perfectly static bubble without any problem. That makes sense? Okay, so this is a pretty boring case. It's a circle. We're looking at numerical errors. Let's do something a bit more physics-based. Let's scroll back up, and let's replace this by what I had before. So what is this? This is modifying the radius by some coefficient, some amplitude, times the cosine of a mode times an angle. This is effectively adding a disturbance on my local radius based on what my angle is. So that's going to allow me to go from this constant radius circle to something that's squished like this, or has potentially multiple lobes. So if I set my mode here, well, to whatever I want to set it to, I should be able to get to different shapes. Here I have it set to 5, so that means I should have 5 lobes. So we can look at what happens. And then I have some amplitude of deformation. I've set it here to 30%, or to a third of my radius. So let's look at this little thing here. So let's run that. Let's go to the initial field. So that's my curvature field, and this is my multiple lobes. So you can see I've imposed 1, 2, 3, 4, 5. So I have a 5-mode cosine perturbation of my local radius by 30% of my radius. So I end up with something that looks like this star-shaped pattern. What should this do under the effect of surface tension? It should be pretty simple. I have a high negative curvature region here and a high positive curvature region here. This should lead to a flow out, and this should lead to a flow in. Depending on your viscosity, this can either oscillate or simply, whoa, sorry. That's what you get when you plot velocity vectors on the crazy scale. So, no. Let me change that scale. There we go. Let's reduce that further. There we go. So there you go. This is the action of surface tension. Okay, so we take this object, take it back to a circular shape through the induced flow field. Provided the deformation is small enough, there are exact solutions for this. So this is in fact a pretty good test case for a surface tension implementation. You can look at the frequency and the decay rate of the oscillation. Let me have some fun with this. A mode 2 should give us an ellipsoid, which should give us the slowest oscillations, because the effective curvature would be the least. So I have now the spill shaped, and you can see it dance around. All right, so any questions on that? That works, right? Okay, so let's move to the second case. So the second case, which I call it density. So I imagine I changed the density, but I'm trying to remember. Let's see. So I have a flow in the second case. Honestly, I can't remember what I did. So I have an inflow going from left to right. Oh yeah, I think I'm just flowing on the droplet. I think I'm just computing a flow on the droplet. Let me check. Yep. I think that's what it is. Okay, so let's look at the differences in code. So the second case is in the demo flow directory. There's very little in the demo flow file. There's very little. I'll just show quickly. I still take this shortcut in the pressure step right here. If we use a level set, then I don't use my standard pressure solver. I go to this ghost fluid based pressure solver. And then the second thing is that I have right here, I have my left velocity set to 1. So I'm going to be flowing from left to right. And then the level set code now has been extended to include this rho star. So there's still the action of surface tension, but now I have this rho star in addition. That requires, so I didn't show you that in the previous file, but in this file you can see I'm specifying a sigma. So I'm specifying a surface tension coefficient. And then the two other parameters that were irrelevant to the single phase flow solver are the liquid density and the gas density. I'm setting here a density ratio of 1 to 1,000. The rest is pretty standard. I've removed this, this multi-lobe shape for my initial droplet, so we're not going to look at the action of surface tension directly. We're going to look at the action of the flow onto that object. So a simple circle. That's my reinitialization, that's my normal, that's my curvature. That's my ghost fluid. The big difference with my ghost fluid this time around is that it starts off by taking my pressure Laplacian and just getting rid of it. Why is that? Because now, since with the variable density problem, or if my liquid and gas densities are not the same, my divergence of 1 over rho grad P becomes a function of time. In particular, the divergence of 1 over rho grad operator, this thing needs to be recreated at every time step based on my new density. Okay, so I start by throwing out this P lap altogether. So I get rid of this. Then I go through the same setup for the ghost fluid problem as before. I sit, so for every grid point, I sit on the middle of my stencil and I move up, down, left, right, and look at point IIJJ. And I look at whether this point is on the other side of the interface. So this is this interface check that I had. Except now, I'm also going to be specifying what my rho star is. So if I'm on the same side of the interface that in both points are positive, I'm going to say that I'm on the liquid side. As a consequence, my rho star, right, the rho star that we derived in our equations, is simply going to be rho liquid. It's the same rho everywhere. I don't need to worry about anything. Everything is in the liquid. I have my rho liquid. And no jump condition. If everything is negative, then everything is in the gas. My rho star becomes rho gas, and I have no jump to worry about. If I'm across the interface, then I need to worry about what rho star is. And for that, I first need to compute this theta that we derived. This theta is the ratio of the interface position to my cell center, where I'm computing the my discretization, divided by the cell size. Essentially, this is a level set weighted interpolation. So that's what this theta is. The rho star is just using theta to do this interpolation. So this is a direct implementation of what we derived, and this is also a direct implementation of what we derived. So theta times rho gas plus 1 minus theta times rho liquid. Maybe we wrote it the other way, but then I just defined theta here as 1 minus theta, but it's the same story. And then I still need to interpolate my jump the same way as before. So I have my jump at cell I, my jump at cell I plus 1 or I minus 1, it doesn't matter, cell I and cell II. Between the two, I know I have an interface. I do linear interpolation weighted by the level set value. Depending on whether I'm on the gas or on the liquid side, I need to either use plus that jump or minus that jump. Because if I'm on the liquid side, I need to subtract the jump. If I'm on the gas side, I need to add the jump. And from this information, I can now recreate my Laplacian operator. So there's two things. What I was doing before is I was just adding to my right-hand side. I still do that. My div, right-hand side, is incremented by my jump times dt times this coef. What is this coef? This coef is 1 over d, my mesh size, so delta x squared, times 1 over rho star. Okay, I'm saying that what will multiply, right? I'm discretizing divergence of 1 over rho grad. Divergence gives me 1 over d, 1 over rho gives me 1 over rho, and grad gives me another 1 over d. So that's what needs to be multiplying everything anyway. So no matter what configuration I'm in, I'm going to be adding that, jump to my right-hand side. But my left-hand side needs to be rebuilt from scratch. So I'll need to build my Laplacian operator. Right now I'm sitting at cell I, looking at cell I, which is either I plus 1 or I minus 1 or j plus 1 or j minus 1. I look at which one it is, so based on the direction and dimension over which I was looping, I decide whether I'm looking at cell I and I plus 1 or I and I minus 1 or or j and j plus 1 and j minus 1. And depending on that, I just recreate my Laplacian operator. So my Laplacian at 0 will get minus this coefficient, which is my diagonal, and my off-diagonal term, my stencil point, will get plus that coefficient. This is what the Laplacian is. The Laplacian is to the right 1 over delta x squared, to the left 1 over delta x squared, in the middle minus 2 over delta x squared. So that's what I do. And minus I minus j plus j. So this is just on the fly building my Laplacian operator, but this guy contains this 1 over rho, where rho is the rho star that we've derived. And that's it. This is, that takes care of setting up the problem. Then I can solve it. This is my cold pressure solve that you can't read here. And then I have to go back and correct my velocity. The correction looks a lot like what we've talked about already, except I also have to be careful about my rho star, because my correction is now minus delta t times 1 over rho star times p minus p over delta x. Well, the p minus p over delta x still requires the use of a jump, so I still will have this plus jump here, but I now need to divide my gradient by rho star. So what I'm doing here is on the fly, I create this rho star as I go using the exact same approach that I discussed before. So this is u. So this is the calculation of the x gradient, x derivative of p, and this is the calculation of the y derivative of p. And then this is it. So this is literally 5 or 6 lines of actual stuff, and then we just recalculate the divergence and we're done. So it's pretty compact. What this should give us is now a full handling, except again for the viscous term that I've left behind. This is a full handling of the viable density in a fully sharp way, as well as a full handling of the surface tension force in a fully sharp way. So I don't remember what I set up as a test case. So let's look. That seems surprisingly short, so let's see. Ooh. So I have a droplet in the middle. Let's do an isosurface. And let's look at the flow field. Okay. Okay, so yes, this was a, so this is just flowing from left to right onto an initially static droplet. So I wonder what the Reynolds number for this is. I should remember, but I don't. So the fluid, the gas is of density 1. The incoming flow is 1 and the radius is 0.15, so the diameter is 0.3. So that's a 0.3 and then divided by the viscosity. What is the viscosity? viscosity is 0.005. So 0.3 divided by 0.005. This is around somewhere of 60. I don't really know what to expect for the flow past the liquid water column at around number of 60. So I don't know really what to expect here. But the point is, the amount of mass in the liquid is enormous compared to that in the gas. And as a result, the gas should feel a significant hindrance due to the pressure, and the momentum, the gas should be deviated around the object, and that's exactly what we see here. So this is indeed behaving like a solid obstacle in the flow, which is what we would have hoped to see. There's some deformation, which might or might not be realistic. So to me, that suggests a few things. First of all, is the surface tension doing anything, or is our numerical diffusion controlling entirely the shape here? I don't know the answer to that question, but we can answer this question by setting the surface tension coefficient to 0. We set the surface tension coefficient to 0, we suddenly don't have any surface tension. Yeah, it's probably a bit more deformation, but not an enormous amount of deformation. Okay. I don't know if we can run with a higher surface tension. So we can try. The code might blow up because there's a CFL limitation associated with it. Now, there you go. You increase the surface tension, you get a significantly reduced deformation. Okay. That's not the most exciting. Although now I'm wondering how high I can go. So I think our simulation is becoming weakly unstable here. I think our pressure solver is probably not converging too well. Yeah, there you go. The surface tension is so high that I'm getting situations where my incomplete Cholesky precondition conjugate gradient solver is not capable of bringing this last column down to anything reasonable. It should bring this down to 0, and it cannot do that. That means that my pressure is not converging if my surface tension is too large. But you can see that indeed with a large surface tension, yeah, it's struggling. We're mitigating the deformation of that object, okay? No surprise here, this is what we would expect. Let's look at the effect of density. What if the density of both phases are the same? That's going to be the most boring simulation ever. Well, maybe not. Oh yeah, the surface tension, so maybe not. Okay, so let me make this the most boring simulation ever. If I don't have surface tension, now I have this interface, no surface tension, same density on both sides. There should be literally nothing happening except this thing gets transported and leaves. That's good news that this is what happens. I can look now at the effect of changing the density. Nothing very significant. Let's do a bigger change. Let's look now at a bubble of gas immersed in liquid. So I'll do that instead of flipping my, well, I could change the sign of my level set. Alternatively, what I'm going to do here is just set my gas density to be 1,000 and my liquid density to 1. That's going to achieve the same thing. Let me turn back on surface tension. So now you can see that the way this bubble curves is the opposite. You're suddenly accelerating this object instead of shearing this droplet like this. You're now accelerating the bubble the other way. We find that it's easier for the liquid, the surrounding liquid, to move faster wherever this gas was present, because there's less inertia preventing this motion. So we find this liquid jetting inside the bubble, breaking it apart. While in the situation of the drop, this was the opposite. The flow was establishing around because it was difficult for the gas flow to push past. The water droplets. Allow me to break this. Let's try breaking this. Let's take 1,000,000 to 1 density ratio. Hey, we broke this. Right away. I think we broke it as well here. So this is a higher density ratio. I think the code blows up. What I'm trying to point out is that the algorithm we have, so at 10 to the 5 it blows up, at 10 to the 4 the behavior is a little strange already. So the point I'm trying to make here is that we're kind of lucky to be able to do, with the ghost fluid method like this, a density ratio of 1,000. This is about as far as an algorithm like that will take us. If we were to start introducing a significant amount of shear at the interface, by, for example, looking at the simulation I showed 2 or 3 days ago of a high-speed gas flow at the surface of a round liquid jet, there's a significant velocity difference between the two that leads to large velocity gradients that you wouldn't be able to run even at the density ratio of 100. So this methodology is fine provided that either the flow is simple enough or provided that the density ratio is sufficiently small. We'll talk about what's going on here in a bit more details, I think, Friday morning. But just so you know, this is not the be-all end-all. There's more steps required to get something that works appropriately. Let me see. I'm wondering if I had something else I wanted to show us this. I don't think so. So let's move to the last case. So the domain size is changed. Oh wait, it's called jet. Yeah, so I remember. Okay. So what I'm doing here is I'm going to create a liquid jet, and we'll start to see. We'll try to see if we can do some breakup with this method. So first exercise in breakup. I've reduced the surface tension coefficient. I have also reduced the density ratio to make my life easier. Okay, so now that I remember what's going on here, let me open it up and we'll modify a few things. So let me show you the inflow conditions. if I can find them. So there's no mask. The flow comes in with a liquid jet centered on 0, extending up to 0.2 above and 0.2 below. I'll turn off everything else. So I'm just going to create a central liquid jet. The corresponding boundary condition that's missing here in our discussion is provided with the initial level set field. The initial level set field looks like this. I have, with the same radius of 0.2, a half circle located at the very entrance of the domain. So I'm going to start my calculation with a little blob of liquid, and I'm going to be flowing right at the location of that little blob. It should just give me a liquid jet coming into my domain. So let's check that first. Let me wait a couple of time units. I don't remember how frequently this thing is outputting. I don't remember how slow it is. I think just a few minutes, but let's open this up. 20 time minutes. Okay, let's see. So I'm going to create a cut. This should just be a straight jet coming from the left with liquid in the middle tracked by a level set. Let's check our level set. It is indeed a half circle initially. If I plot the isosurface, that's this thing. Then I can color now by the velocity, and you can see that the velocity is indeed coming in from the left. So let me reopen this. It will have progressed a bit further. And we'll make a comment on this, and then we'll move on to a bit more exciting of a case. So this is pretty boring. There's not too much going on. This is a fairly slow-moving jet, and you can see that we're forming some sort of a mushroom cap. Well, this is what it is for our set of equations. No particular comment on that. If you were very, very generous, you could say that this is the first attempt at the 2D model of a straight, round pressure jet that you could find, for example, in diesel injection. Straight, round jet, you're shooting forward an amount of liquid. The induced shear at the surface should lead to breakup. But we can't possibly get to breakup conditions with the little code we have. We would need to be able to have higher resolution so that we can go to higher amounts of shear and higher velocities and higher Reynolds numbers. But overall, the main feature that you would expect that you can see, I think I saw that in the front page of your course pack book, is that your jet, as it gets issued into a domain, it should form some sort of a mushroom cap shape. And that's indeed what we get right here. Because we can't reach a high enough, oh, this thing finished, let me take a look. Because we can't go to a high enough injection velocity, we cannot impart enough momentum to this liquid jet. There are other ways you can achieve liquid breakup. So there you go, not particularly exciting. There are other ways that you can achieve liquid breakup if you give momentum to something else than your liquid. And that's this image I was showing again at the beginning of our discussion 2 or 3 days ago. This jet that we were looking at was atomizing because of the fast co-flow of gas. So now what we're going to do is we're going to put our momentum into gas and let the liquid go slowly. The way we're going to do this is by giving exactly the same initial condition with the level set, but now around my liquid, I'm going to tell my gas to go 10 times faster above and below. And then in order to feed to feed momentum to this system, I'm going to provide a little bit of a co-flow above and below. So I'm going to make sure that I don't just establish a big recirculation region. So the main difference here is that now we're not hoping to break this jet just through its own momentum. We're using the momentum of the second phase to break this jet apart. The big trick here is that now the gas phase carries a non-negligible amount of momentum. It goes 10 times faster. But its density is set to be a tenth. So my liquid density is 10, my gas density is 1. My liquid velocity is 0.5, I think. My gas velocity is 5. So that means I effectively have the same momentum in both phases. The rate at which I'm injecting momentum with both phases is about the same. So from a dynamic pressure ratio perspective, from the perspective of how much oomph the fluid carries, the gas now should be able to distort the liquid because it carries as much momentum. Computationally, we're getting into a pretty tricky realm here, which is that we have fast-moving light stuff impacting slow-moving heavy stuff. So the pressure should be the same, approximately, but for different reasons. This is where if we start cranking up the density, the code will start suffering a lot and will probably become unstable. So let me recolor or reset the range for my velocity. So we haven't discussed about this in details yet, and we will discuss about that tomorrow morning. But we have on Monday talked about flow stability. And in particular, we said that in a situation where, come on, move with me. There you go. I really wish I could make this, isosurface thicker. I don't know why this is not working. Anyway. Well, that works. Okay, sure, fine, we'll do that. So, now this way you can see. Remember what we were talking about on Monday? We said shear exposed to a two-phase system like that should give rise, even in the absence of a density ratio, to a Kelvin-Helmholtz instability. We said that the density ratio would change the convection velocity of the wave. It would, I shouldn't say convection, I should say the wave speed. This was the Demotakis wave speed that was mass averaged, or density averaged. So if we change the density between the two phases, this will change the velocity at which surface waves will transport. But this flow, because right here I'm going faster than here, that flow should be subject to a Kelvin-Helmholtz instability, or Kelvin-Helmholtz type. Kelvin-Helmholtz is really the name for constant density. Surface tension should stabilize that, but I think I either turned it off or made it small enough that it doesn't play a role here. So if surface tension doesn't stabilize that, I don't have gravity here, so there's no Rayleigh-Taylor type of problem. We don't have to worry about any of that. What we should see is surface waves. And I would argue, well, let me play this, but I would argue that this is exactly what we see. They're initially synchronized between top and bottom. You can see those surface waves being released, and they're getting convective downstream as they grow. The other thing you can see, if you zoom out a bit, is that, that's not zooming out, that's stopping the movie. So that's zooming out. The other thing you can see is that those waves at some point become synchronized, and in fact the dynamics on one side start to couple to the dynamics on the other side. So we go from those symmetric wave dynamics to a situation where we start flapping around. Those flapping dynamics are expected in planar liquid jets like this. This is not a particularly surprising thing to see. It's kind of reasonable for us to see that. I'd like also to point out that what we're doing here involves breakup. For the first time, we're looking at how our interface gets pulled into ligaments. You can see those little ligaments coming off and start forming separated droplets. But in 2D, that shouldn't really happen. There's nothing that supports breakup of a 2D liquid structure. A 2D ligament is not susceptible to the Rayleigh plateau instability we talked about on Monday. A 3D ligament, you can pull on it, and if you perturb it, it can become unstable and break into droplets. It is a reasonable thing to expect to happen, and as a result, seeing droplets is fine. Here, the only reason why this guy is separated from the rest is because of the limited resolution provided by our mesh, combined with numerical errors. So we're not doing physics here, we're playing with our code. Let's follow this little guy for a second. Okay, so we have the separated liquid structure, what you might want to call a droplet. Let's move forward one time step, another one. You can still see it. It's noticeably becoming smaller, and now it's gone. So over the course of a few time steps, this large structure that broke apart because of lack of mesh resolution, and we can zoom in and see that indeed what's happening right here is that we're reaching exactly the point where we have just one cell separating the two interfaces. We get a small structure, but that small structure is now represented by a level set that suffers from numerical diffusion. Remember what we said the level set shape is for a circle like this. It's about a conical shape. The conical shape is characterized by the fact that at the very tip, it exhibits a corner. That corner is not going to be the friend of the third order upwind biased quick that we're using. It's not going to be the friend of the third order we know good enough discretizations that we are using for our reinitialization. Those schemes are going to keep on rounding this off. As a result, we'll keep on diffusing away this sharp feature, and the consequence is the numerical diffusion will keep shrinking the size of this thing. So this is, as soon as you start looking at breakup type of problems, it becomes absolutely obvious what is one of the main flaws of level sets. And that is the fact that numerical diffusion actively acts towards making small structures disappear. Well, if those small structures are numerical oscillations at the surface, well, having them disappear or not appear as strongly is not, you don't lose sleep over that. If you're computing a spray, the entire point is that you want to generate those small structures. If your method actively works at removing those, essentially, whatever your flow rate here is, you're going to end up with essentially no liquid mass at the exit. And this is what I wanted to point out, and specifically with this case. Look at the enormous difference between the flow rate of liquid coming in and the flow rate of stuff coming out. There's almost no liquid mass coming out because almost all of it disappears due to the effect of numerical diffusion. Okay, so this, I think, should be, and well, we really could go one step further, and that wouldn't be complicated to do, but if we were to integrate over that line and look at the true rate at which mass leaves, liquid mass or liquid volume leaves, compared to the rate at which we inject it, it would be probably an order of magnitude below. If we were to extend the domain, it would be even worse. In fact, if we were to simply create a little droplet, 10 cells in diameter, say, and transport it in the periodic domain, it would not survive travel by more than maybe 10 or 20 times its own diameter. It would just shrink slowly until it disappears. So atomization with level sets, that is a real problem. If you're looking at a process by which you generate small-scale features, level sets are probably going to be a big problem. If you're interested in a droplet that bounces off another droplet, if you're interested in maybe looking at a single drop evaporation, if you're interested in looking at rolling droplets on an inclined plane, those problems are probably very much appropriate to look at using level sets. If you're interested in spray atomization, yeah, stay away. I think, so let me see, we ran this, that ran, I'll do just one last thing if you allow me. I'll go back here and I will increase the density ratio. I'm running at a density ratio of 10. It's not really a liquid gas density ratio. Well, you could argue a density ratio of 30 maybe gets you into the realm of diesel fuel injection. 100 gets you into the realm of a pressurized gas turbine type of problem. So what I wanted to see just happened. I don't know if you were following the U velocity, the one I'm circling here. It jumped from being on the order of 7 to 8 to suddenly being on the order of 30. I'll generate one more timestamp of data if I can. Stop blowing up. Come on. We're not going to make it. Yes, we are. We made it, okay. So what happened here? The flow is unstable, it does its thing, no particular problem, and then boom. What is going on? It looks beautiful, it almost looks like we're doing combustion, but no, this is just random numbers. You can see the flow velocity here is going to creep back up and push against the liquid until everything blows up. This is showing up with a velocity ratio of 10 between my phases and a density ratio of 100. So now I've imparted 10 times more momentum to my gas phase than to my liquid phase. Now I should get into some serious atomization regime. Now my gas is really capable of tearing apart this liquid. It has 10 times more momentum. It can push it away. Fine, it should be able to do that, but what we see is also the scheme becomes unstable. So in this case, in fact, it's not that easy to see. I would have to probably, well, let me restart with a slightly lower value while I explain what's going on. Let me try maybe 50. So that we can run a bit longer and still see. So you see, this is what you have to look at. 7, 8, 9, 10 is fine. But it will probably jump pretty soon to 20 or 30. Yeah, we're around 20 and we're going to go to 30. So this is probably already misbehaving. What we're going to see, it would be nice if in fact we could visualize this directly. Yeah, it's not any better. Sorry, let's take one last attempt at 20. See how bad it needs to go. Oh, there we go. So, that's very much the type of stuff that I wanted to talk about. What we just saw, let me plot that using the velocity vector. I'm going to undersample it. You can see that we've created a little vortex here where the flow field going back is enormous. Why is the flow capable of pushing back inside like this? Well, the reason for it is because the way we formulated our problem right now is we're solving for velocity using a non-conservative form of the momentum equation. We've divided throughout by our density, and we've brought the density as a 1 over rho grad p. That means that we're solving for velocity. We're not conserving momentum in any way. In fact, the momentum would have to be obtained by multiplying the effective density we've used in our pressure equation to the equation we wrote for the velocity, essentially. Now, let's think about how we obtain our mass. Our mass is, our volume, our local density, is obtained from transporting our level sets. We talked about this process. It is a non-trivial process that involves multiple steps, including a reinitialization equation. That tells us where our mass is. What tells us where our velocity is a solution using our Adams-Bash force and centered derivatives. It's a solution of our Navier-Stokes equation. That means that I have no consistency whatsoever between the way mass moves around in my system and the way momentum moves around in my system. Effectively, if I were to keep track of the local momentum, I'd find that it is completely spuriously fluctuating depending on how my velocity gradients move with respect to my local level set. So the simplest way to think about how to break the code because of this is the following. I have high-speed gas, low-speed liquid, heavy liquid, light gas. If I misplace the interface between fast and slow and the interface between heavy and light, I can spuriously create momentum as much as I want. And I have no way of controlling the relative motion of these two because I use two different schemes to transport my velocity gradient and to transport my distribution of mass. So if my level set creeps in a little bit up into my high-speed gas region, which is exactly what happens here, what will develop is a region of enormous momentum, high velocity and high density. And that region of high momentum will blow everything apart. So we're going to have to start worrying very much about how we treat the left-hand side of Navier-Stokes. Going to the non-conservative form is fine provided that you have either low shear or low density ratios. If you want to be stable with high shear or high density ratio or both, you need to have a consistent way of advecting momentum as you have of advecting mass. So, and I'll talk about how to do that on Friday, and for now, I think this is it. Any questions on this stuff? So what we'll do tomorrow is, starting from this observation that this is not good enough and it loses all the mass, we'll put together a method that will not lose all the mass. Okay, so that's going to be the rough work we do tomorrow. All right, thank you for your attention, and I'll see you tomorrow morning.